All right, so June 26th, 1897, Spithead, off the coast of Portsmouth, England, Queen Victoria's Diamond Jubilee Naval Review, the most powerful armada ever assembled, 165 warships from the Royal Navy and fleets from around the world, all lined up in perfect formation, stretching for miles across the water. Admirals in full dress uniform, dignitaries, the press, everyone who mattered in British society was there to witness this spectacular display of imperial might. And then, this small, sleek vessel just appears. No one invited it. No one authorized it. It comes tearing through the review lines at a speed that makes every single person watching go absolutely silent. Because nothing, and I mean nothing, should be moving that fast on water. Not in 1897. The Royal Navy patrol boats try to intercept this. They chase after this intruder at full steam, coal smoke pouring from their stacks, engines hammering away, and they can't even get close. This mysterious boat is doing 34 knots. 34! The fastest warships in the world could barely manage 27. The vessel's name was Turbinia, and the man standing on her deck watching the patrol boats fall farther and farther behind was Charles Algernon Parsons. He'd just crashed the most important naval event of the century to prove a point, and that point was every single ship in that massive fleet was already obsolete. Now, let's back up a bit, because to understand why Parsons did something so audacious, so completely insane from a career perspective, you need to understand the problem he was trying to solve, and that problem was steam power itself. See, by the 1880s, steam engines were everywhere. They powered factories, trains, ships, everything that drove the industrial world. But they all used the same basic principle: reciprocating engines. Pistons moving back and forth, converting the pressure of steam into mechanical motion through a crankshaft. And this design had hit a wall. Think about it. You've got steam pushing a piston forward, then the piston has to stop, reverse direction, and push back the other way. Then stop again, then forward again. All that starting and stopping, all that back and forth hammering, it was violent, it was inefficient, and it limited how fast you could go with the engine, because the faster you tried to go, the more those massive pistons wanted to shake the whole machine apart. Ships were especially limited. The biggest marine engines were these enormous monsters, sometimes weighing hundreds of tons, just to produce a few thousand horsepower. They vibrated so much that the entire ship would shudder. They broke down constantly, and they couldn't run fast enough to drive ships at really high speeds without literally tearing themselves to pieces. Parsons looked at this problem and thought, what if we don't need pistons at all? What if instead of trying to make steam push something back and forth, we just let it flow? Let it spin continuously, smoothly, in one direction. No stopping, no reversing, no hammering. What if we built a turbine? Now, this wasn't a new idea. People had been trying to build steam turbines for decades. The concept was simple enough. Take a wheel with blades on it, like a water wheel, and blast steam at the blades. The steam pushes the blades, the wheel spins. Easy, right? Except it wasn't easy. At all. Every steam turbine that had been built up to this point was, frankly, terrible. They were inefficient, they broke constantly, and they couldn't produce anywhere near the power of a good reciprocating engine. Most engineers had given up on the idea. Steam turbines were theoretically interesting, but practically useless. Charles Parsons was born in 1854 into the Anglo-Irish aristocracy. His father was the 3rd Earl of Rose, a distinguished astronomer who'd built the largest telescope in the world at the time. So Parsons grew up around precision engineering, around people who didn't accept that something couldn't be done just because everyone else had failed at it. He studied mathematics at Cambridge, then took apprenticeships at engineering firms, learning how real machines were actually built and operated. By the early 30s, he was chief electrical engineer at Clark Chapman and Company in Newcastle, and it was there, in the early 1880s, that he started thinking seriously about turbines. The fundamental problem with every previous turbine design was this: if you tried to extract all the energy from high-pressure steam in one stage, in one wheel, the blades would have to spin at absolutely insane speeds to be efficient. We're talking tens of thousands of revolutions per minute. And at those speeds, the centrifugal forces would just rip the blades right off the wheel. Parsons' insight was elegantly simple. Don't try to extract all the energy at once. Use multiple stages. Let the steam expand gradually, passing through wheel after wheel after wheel, each one extracting a bit more energy, each one running at a practical speed. He designed his first turbine in 1884. It was small, just 10 horsepower, meant to drive an electrical generator. It had 15 stages, 15 sets of blades, with the steam flowing through all of them in sequence. And when they tested it, it actually worked. It ran smoothly, quietly, efficiently, at 7,200 revolutions per minute with none of the vibration, none of the hammering, none of the mechanical violence of a reciprocating engine. So Parsons had proven the concept. His multi-stage turbine worked. But working in a small scale and working at an industrial scale, those are very different things. And this is where the story gets interesting, because Parsons didn't just have to solve engineering problems. He had to fight the entire established power industry. See, Clark Chapman and Company wasn't particularly interested in turbines. They built reciprocating engines. That's what they knew. That's what their customers wanted. Parsons kept pushing for more turbine development, and the company kept saying no. So, in 1889, he did what any engineer with aristocratic connections would do. He quit, borrowed money from his wife's family, and started his own company. The C.A. Parsons and Company set up shop in Newcastle, and their first major product was a 300-kilowatt turbo generator for power stations. 300 kilowatts might not sound like much now, but in 1990, that was serious power, and the advantages were immediately obvious. The turbine was compact, it was quiet, it didn't shake the building, it could run continuously for weeks without stopping, and most importantly, it was efficient. A reciprocating steam engine of that era might convert 12 or 13% of the steam's energy into mechanical work. Parsons' turbine was hitting 15–16%. That difference might not sound huge, but in power generation, every percentage point matters. That's money, that's coal you don't have to buy. That's power you can sell instead of wasting as heat. Power stations started buying Parsons' turbines, first in Britain, then across Europe. By the mid-1990s, his company was thriving, but Parsons had a bigger vision. If turbines could revolutionize electrical power generation, why couldn't they revolutionize marine propulsion? This is where it gets complicated, because marine propulsion is a completely different challenge. On land, you can run your turbine at whatever speed is most efficient, and use gears to adjust the final output. But in 1894, there were no gears strong enough to handle the power levels Parsons wanted to use, so the turbine had to run the propeller directly, which meant the turbine had to run at propeller speeds, somewhere around 1,000 revolutions per minute. Parsons designed a new turbine specifically for marine use, longer with more stages, optimized for lower speeds. And then he did something that still seems crazy. He personally financed the construction of an experimental vessel to test it. He sank his own money into building Turbinia. The ship was 100 feet long, 9 feet wide, basically a floating test platform shaped like a steel knife. The first turbine he installed drove a single propeller shaft, and when they tested it in 1894, it was a disaster. The ship barely hit 20 knots. Something was wrong. Parsons, being Parsons, didn't give up. He started experimenting. He built a test tank at his company, a long trough where he could test scale models of propellers at high speeds. And what he discovered changed everything. At high speeds, propellers cavitate. The blades spin so fast that they create low pressure zones in the water, and the water literally boils, forming vapor bubbles. These bubbles collapse violently, creating shock waves that destroy the propeller and critically rob the propeller of thrust. The faster you try to spin the propeller, the worse it gets. Above a certain speed, you're just churning the water into foam and getting nowhere. The solution? Don't use one big propeller, use multiple smaller propellers on multiple shafts. Each propeller runs at a lower speed, below the cavitation threshold, but combined they can absorb all the power the turbine produces. Parsons rebuilt Turbinia with 3 propeller shafts. Each shaft had 3 propellers mounted in series, 9 propellers total. The turbine was split into 3 sections, each driving one shaft. And when they tested this configuration, the ship exploded forward, 32 knots, 34 knots, faster than any vessel afloat. Now, here's where Parsons faced his biggest problem. He had a revolutionary propulsion system. He had proof that it worked, and nobody cared. The Royal Navy wasn't interested. Commercial shipping companies weren't interested. They all said the same thing. Reciprocating engines work fine. They're reliable. We know how to maintain them. Why would we switch to something new? This was more than just technological conservatism. There were financial interests at stake. The big marine engineering firms, the ones that built reciprocating engines, they weren't about to admit that their entire product line was obsolete. They spread doubt, they questioned Parsons' test results. They suggested the turbine might work for a small experimental vessel, but couldn't possibly scale up to real ships. Parsons needed to force the issue. He needed a demonstration so dramatic, so undeniable, that no one could ignore it. Which brings us back to June 1897 and Queen Victoria's Diamond Jubilee Naval Review. So Parsons takes Turbinia to Spithead, uninvited, and crashes the review. And the reaction was, well, it was everything he'd hoped for. The press went wild. The Times, the Daily Telegraph, papers across Britain ran headlines about this mysterious speedboat that had embarrassed the Royal Navy. Naval architects who dismissed Parsons suddenly wanted meetings. Within weeks, the Admiralty quietly contacted him about possible applications for turbines in warships. But we need to understand what Parsons had actually achieved technically. Because the turbine itself, the machinery inside Turbinia, that was the real revolution. Let me walk you through how it worked. Inside the hull were 3 separate turbine units, arranged in series. The steam entered the first turbine at high pressure, somewhere around 150 pounds per square inch, and started flowing through the stages. Each stage consisted of 2 sets of blades. The first set, the nozzles or guide vanes, were fixed to the casing. They directed the steam onto the second set, the rotor blades, which were mounted on the spinning shaft. As the steam hit the rotor blades, it pushed them, transferring energy to the shaft. But here's the clever part. As the steam expanded through each stage, it lost pressure and gained volume. So each successive stage had to be slightly larger in diameter to handle the increasing volume of steam. The whole turbine assembly looked like a series of graduated cylinders, each one bigger than the last. By the time the steam exited the final stage, it had expanded from 150 pounds per square inch down to nearly atmospheric pressure, roughly 15 pounds. Almost all of the energy had been extracted. The exhaust steam went to a condenser, turned back into water, and got pumped back to the boiler to start the cycle again. The entire turbine unit, all 3 sections, weighed about 15 tons and produced 2,000 horsepower. A reciprocating engine producing the same power would have weighed 3 or 4 times as much and taken up far more space. And the turbines ran at speeds that would have destroyed a reciprocating engine, smooth and steady, hour after hour. Now, the Navy was interested, but they weren't about to start installing turbines in battleships based on one demonstration. They wanted proof that turbines could work in real warships under combat conditions. So Parsons struck a deal with the Admiralty to build 2 turbine-powered destroyers as trials vessels. The destroyer Viper was launched in 1999. It had Parsons turbines producing 12,000 horsepower, driving 4 propeller shafts. On trials, it hit 37 knots, making it the fastest warship in a world. The second destroyer, Cobra, was even faster, touching 39 knots. The Navy was impressed. But then, disaster. In 1901, Viper ran aground in fog off the Channel Islands and broke apart.
A few months later, Cobra broke in half during rough seas in the North Sea and sunk, killing most of her crew. The press blamed the turbines. Naval conservatives said this proved turbines were too dangerous for warships. Parsons' enemies said the high speeds created by turbines put stresses on the hull that traditional ships couldn't handle. The whole turbine program looked like it might collapse. Except the actual investigations showed something different. The turbines hadn't caused either disaster. Viper had simply hit rocks and fog, nothing to do with her propulsion. Cobra's hull had a structural weakness, a design flaw in her construction that would have eventually failed regardless of what engines she had. The turbines themselves had performed flawlessly, but the damage was done to public perception. The Navy quietly kept studying turbines, but they weren't rushing to adopt them. So Parsons did something brilliant. He approached the civil shipbuilding industry. The Cunard Line was planning 2 new passenger liners, massive ships meant to compete with German vessels for dominance of the transatlantic trade. Parsons convinced Cunard that turbines were the future. They were quieter, smoother, more efficient, and most importantly, they could push a ship faster than reciprocating engines. In 1905, the Cunard liner Carmania was launched, powered by Parsons turbines. Her sister ship, Caronia, was identical in every way, except she had traditional reciprocating engines. Perfect test case. And Carmania was faster, smoother, and more economical. She burned less coal. She vibrated less, making the passenger experience better. The turbines needed less maintenance. The results convinced Cunard. Their next 2 liners, Lusitania and Mauretania, both got turbines. Mauretania's turbines produced 70,000 horsepower, driving 4 propeller shafts, pushing the ship to 26 knots. She held the blue ribbon speed record for the transatlantic crossing for 20 years. Now the Royal Navy couldn't ignore turbines anymore. If civil liners were using them successfully, warships certainly could. The battleship Dreadnought, launched in 1906, was the first major warship with turbine propulsion. 18,000 horsepower, 21 knots. She made every existing battleship obsolete overnight, not just because of her armament, but because she was faster, more maneuverable, more efficient than anything else afloat.
So by 1910, turbines had basically taken over marine propulsion. Every major navy in the world was building turbine-powered warships. Passenger liners, cargo ships, even smaller vessels were switching to turbines. Parsons' company was building turbines for ships worldwide. But the bigger revolution, the one that really changed civilization, was happening on land. Remember, Parsons had started with electrical power generation. That was his first application for turbines. And while everyone was focused on the dramatic marine applications, power stations were quietly transforming. A reciprocating steam engine driving a generator is inherently inefficient. The engine runs at maybe 200 revolutions per minute. The generator needs to run at several thousand. So you need all these belts and gears and clutches to match the speeds, and every connection loses energy to friction and heat. Plus, the engine itself is only converting maybe 12% of the steam's energy into useful work. A turbine can drive the generator directly, no belts, no gears, both running at the same speed, and turbine efficiency kept improving. By 1900, Parsons turbines were hitting 20% thermal efficiency. By 1910, 25%. That might not sound dramatic, but think about what it means. For the same amount of coal, you're getting twice as much electricity compared to the old reciprocating engines. This made electric power affordable, and that changed everything. Electric lighting spread beyond wealthy homes and commercial districts. Electric streetcars replaced horse-drawn transportation in cities. Factories that had run on mechanical belt drives from central steam engines could now put individual electric motors on each machine, completely reorganizing how manufacturing worked. The scale increased exponentially. In 1900, a large power station might have a few generators producing a few hundred kilowatts. By 1914, stations were installing turbines producing 10, 15, even 20,000 kilowatts each. The Fisk Street Station in Chicago, opened in 1903, had Parsons turbines. The Hellgate Station in New York, 1909, Parsons turbines. Across Europe, from Berlin to Paris to London, turbines were becoming standard.
And here's something interesting. As turbines got bigger and more powerful, engineers discovered they could use multiple turbines in series, just like Parsons had done in Turbinia. High-pressure steam would enter the first turbine, partially expand, then exhaust into a larger intermediate pressure turbine, then into an even larger low-pressure turbine, each stage optimized for its pressure range. These compound turbines pushed efficiency even higher, above 30% by the 1920s. Parsons kept innovating. In 1910, he introduced geared turbines for ships, solving the problem he'd avoided back in the 1990s by developing gears strong enough to handle the power. This meant the turbine could run at its optimal speed, maybe 8 or 10,000 revolutions per minute, while the propeller ran at just a few hundred. Even better efficiency, even more power from the same size turbine. He experimented with different working fluids. Most turbines used steam from coal-fired boilers, but what about other options? He tried turbines powered by internal combustion engines, using the hot exhaust gases to drive the turbine. This didn't work well with the materials available in his lifetime, but he was anticipating gas turbines, the technology that would later power jet aircraft and modern power plants. By the time World War I started in 1914, turbines were everywhere in the war effort. British battleships, German U-boats, American destroyers, all turbine-powered. Electrical power from munitions factories, shipyards, military bases, almost all generated by turbines. The industrial capacity that allowed Britain and its allies to eventually overwhelm Germany was built on turbine technology. Parsons was knighted in 1911, became a baronet in 1919. He received honorary degrees from universities across Europe. The Institution of Mechanical Engineers, the Royal Society, every major engineering organization recognized his contributions, but he never stopped working. He was in his workshop, still designing, still experimenting, into his 70s. The companies that built turbines, they all licensed Parsons patents. General Electric in America, Brown Boveri in Switzerland, AEG in Germany. Every major electrical manufacturer was building Parsons-type turbines. The design had become universal, and as turbine technology matured, as metallurgy improved, as engineers learned to run turbines at higher temperatures and pressures, efficiency kept climbing.
Charles Parsons died in 1931 at 76 while on a cruise. By then, his turbines were generating probably 80% of the world's electricity. Marine steam turbines were in virtually every major ship afloat. The technology he'd pioneered had become so fundamental to modern civilization that most people didn't even think about it. But here's what's remarkable. We're still using his invention, right now, today. If you flip on a light switch, odds are very good that the light powering that light came from a turbine that works on exactly the same principles Parsons developed in the 1880s. Modern steam turbines in power plants produce 1 million kilowatts or more, thousands of times more powerful than anything Parsons built. They're made from exotic alloys that can handle temperatures and pressures he couldn't have imagined. They're controlled by computers, monitored by sensors, optimized by artificial intelligence, but fundamentally, they're still multi-stage reaction turbines, steam flowing through wheel after wheel, expanding and losing pressure, transferring energy to a spinning shaft. About 60% of the world's electricity still comes from steam turbines. Coal plants, natural gas plants, nuclear plants, they all use turbines. A nuclear reactor is just a very elaborate way of boiling water. That steam drives a turbine. Same principle. Even renewable energy uses turbines. Geothermal plants, concentrated solar thermal plants. Anywhere you're generating steam, you're using turbine technology that descends directly from Parsons' work. Gas turbines, the kind that power jet aircraft and modern power plants, those evolved from Parsons' experiments. He never got them working properly with the materials he had, but the multi-stage axial flow design, that came from steam turbines. The first practical gas turbines in the 1930s were basically steam turbines modified to run on hot combustion gases. And marine turbines, even though most modern ships use diesel engines, the biggest, fastest vessels still use turbines. Nuclear-powered aircraft carriers, submarines, they use steam turbines. Nuclear reactors heating water, steam driving turbines. Liquefied natural gas carriers, some of them use turbines running on boil-off gas.
The fastest passenger ships still use turbines. What Parsons really gave us was this. He proved that continuous rotary motion is fundamentally more efficient than reciprocating motion for converting energy. Every piston engine has to waste energy stopping and starting, reversing direction. A turbine just spins, smooth and continuous. That insight changed everything. He also proved that patient, systematic engineering could solve problems that everyone else had given up on. Steam turbines had been failing for decades before Parsons. Everyone knew they didn't work. He looked at why they didn't work and fixed each problem methodically. Multiple stages to handle the expansion of steam, careful blade design to extract maximum energy, proper materials to handle the stresses, testing, measurement, refinement. And the Turbinia demonstration, that audacious stunt at the Naval Review, that taught us something too. Sometimes, when you've got something revolutionary, you can't wait for permission. You can't wait for people to understand. You have to show them. You have to make it undeniable. Parsons' legacy isn't just the turbines themselves, it's the approach. Solve the physics first. Build something that works. Test it, measure it, improve it, and then make people pay attention whatever it takes. Every time you turn on the lights, you're benefiting from Parsons' work. Every time you fly in a jet aircraft, that's turbine technology. Every time a city keeps running because the power plants keep generating electricity, that's his vision made real. He took an idea that everyone else had abandoned and turned it into one of the foundations of industrial civilization. Not bad for a guy who crashed a party at Spithead.